Okay, so far what we've talked about is we've looked at sampling distributions in general. We've talked about what is a sampling distribution. We've constructed some sampling distributions for sample mean or sample range. Those were kind of the two most common ones. And then we talked about what it means to be biased and unbiased. In terms of biased and unbiased, I said you need to be able to tell looking at graphs if a statistic is biased or not. And then you need to just know some of the more common ones. So the biggest unbiased statistics are sample mean, sample proportion, and sample variance. We don't do a lot with variance, so we are going to focus on mean and standard deviation. There is a lot we know about how X bar or how sample mean works. There are 4 properties that you need to know for the sampling distribution for sample mean, so for X bar. The first one you already know. If you take all of those X bars and you average them, you're going to get the population mean. So if you take all of the X bars of the same sample size and you average them, you'll get the population mean. And that is because sample mean is unbiased. It's an unbiased estimator of the population mean. The one that is new to us, if we take all of those sample means and we find the standard deviation. So if we take all of those sample means and we find the standard deviation, that is equal to the standard deviation of the population divided by root n. Okay, so what we see is if we take bigger sample sizes, our standard deviation in general will be smaller, the standard deviation of the X bars. So this relates to center, spread, and then the other two are shape. If the population is normally distributed, then the sampling distribution is also going to be normal, regardless of whatever the sample size is.
Is n in that the size of the sample?
Yes.
For the X?
Yes. So not how many of them there are, but how big each individual sample is.
So even though we know that like the standard deviation of the mean samples is equal to the whatever we're at, or square n,
Yep.
like does that still mean it's biased because we have to do something to it?
No. Bias just has to do with the center.
Okay.
Bias only has to do with the center, not with the spread.
Is the standard deviation also biased?
Sample standard deviation, so S is biased. Population or sample variance is unbiased. But this is the measure from the population. So there is no bias. It's not something that we're estimating. Okay, and then the one that is really, really, really important, central limit theorem. Central limit theorem says, if our sample size is large, which is considered above 30, the sampling distribution of X bar is approximately normal, regardless of what the population looks like. The central limit theorem is the basis of what we do second semester. It's a very, very powerful theorem. And some of you actually know someone that proved or did some significant research and studies into the central limit theorem. Not me. Any of you in here had Mr. Hammond?
I have actually.
Okay, if you had Mr. Hammond, when he was in grad school, he did a lot of studying into the central limit theorem. So if you ever want to learn more, go talk to him because he loves the central limit theorem. Okay. This is going to mean nothing to you yet until we see some examples. Okay. So if the population is normal and we take small sample sizes, it doesn't matter, X bar is still going to be normal. So if the population is normal, it doesn't matter the size of the sample that we will take, but those sampling distributions will be normal. If the population is not normal, though, the population is skewed, the population is bimodal, something like that. if we take a small sample size, then X bar will generally follow the population shape. But of course with a smaller spread. That's not a hard, fast rule, but that's generally what happens. And then if we have a large sample size, doesn't matter what the population looks like, X bar will be approximately normal. And that's because of the central limit theorem. That is what you need to know. At this point, we just need to practice. Okay, so let's look at an example here. ACT scores are approximately normally distributed with a mean of 22.1 and a standard deviation of 4.7. What is the probability that a randomly selected sample of 5 students will have an average score of at least 25? When you read this, the first thing you should do, like we've been talking about, define a variable and put things symbolically, whichever numbers you were given. So let's say that X is ACT score, a student's ACT score. We know that X is normal with a mean of 22.1 and a standard deviation of 4.7. So that is the first sentence. Okay. This is the key part here, is writing the question in probability notation. So it says, what is the probability that a randomly selected sample of 5 students will have an average score of at least 25? So what a lot of people want to do is they want to say, I'm going to find the probability that one student has a score of at least 25. And then I'm going to raise that to the 5th power. Whatever that number is, what is the meaning of this probability? What's the meaning of that probability? X is at least 25, but then raising to the 5th power. All 5 students have scores of at least 25. That's not what we're asked. What we are asked is for a sample that has an average. So that's not what we want. Instead, what we want is the probability of X bar to be at least 25. What that tells us then is we are looking at the distribution of X bar, not of X. Not of X. So we need to talk about X bar then. First thing we know, X bar. Because X is normal, X bar then is also normal. We know that the mean of X bar is equal to the mean of the population. So the mean of X bar then is 22.1. And the standard deviation of X bar is the standard deviation of the population over root n. So in our case, the standard deviation is 4.7 over the square root of 5. Now it's just a regular normal problem. I'm looking for the probability of being at least 25 with this mean and that standard deviation. So let's draw ourselves a figure and then we'll go to the calculator. So we're going to do the 0, 1, 2 like we normally do. And then I do 22.1. 4.7 divided by the square root of 5 is about 2.1. So this is going to give us 24.2 and 26.3. So again, that number is about 2.1. So this will give us 20, and this will give us 17.9. So then 25 is about here, and we are looking for at least that. if you now would go to your calculator to calculate this, what function are we going to go to? Inverse norm or normal CDF? Normal CDF. Okay, so do normal CDF, put in the numbers you have, and let's see what we get. I get about 0.084. That's what you're doing this unit. So that is the probability if we take 5 students at random that their average score will be at least 25. So that if I asked you, would that be surprising? Would it be surprising to have a sample of 5 students and the average score be at least 25? What would you tell me? What's the cutoff for surprising? 5%. 5%. So this would not be very surprising. Okay, questions before we do one more example on our together, and then you guys are going to do one. Okay, next page. There are 2 examples. This first example lays everything out for you step by step. The second example is the one that you are going to do, which doesn't lay it out step by step for you. So this first one is the one that I want us to do together. A bank in a small town has to stock its single automated teller machine, ATM, with cash at the beginning of each day. Based on thousands of transactions in the past year, they know that the average amount of money requested by a customer is $87, with a standard deviation of $52. The distribution of money requested is strongly skewed to the right. The bank estimates that there will be 50 customer requests for cash from the ATM each day. The bank is trying to decide how much total cash should be stocked in the machine at the beginning of each day. Calculate the probability that a random sample of 50 customer requests for cash would require a total of $5,000 or more, which is an average request of $100 per customer. Okay, so first thing we're going to do is we're going to write this in probability notation. So, random sample of 50 customer requests has an average request of $100 or more. So we are looking for the probability that X bar is at least 100. Once you have that probability, it should guide your work from there. We need to know about X bar. We need to know the center, the shape, and the spread. So we know that X bar, the mean of X bar, is going to be equal to the mean of the population. Well, we are told that from the past year, the average amount was $87. Then the standard deviation of X bar is the standard deviation of the population over root n. So that would be that $52 over the square root of 50. Then talking about shape. Is the distribution of X bar normal? Last question we were told the population is normal, which means the sampling distribution has to be normal. In this case, though, the population is skewed to the right. Danny? Sample size is above 30. So we would say X bar is approximately normal with a mean of 87 and a standard deviation of 52 over root 50. And again, the reason that X bar is normal is by the central limit theorem, because our sample size of 50 is bigger than our sample size of 30. Okay, so now we're going to calculate the probability. So you're going to do this right now. You're calculating this probability with this mean, this standard deviation. So do that real quick in the calculator. We're not going to draw a figure because I'm a little lazy, but do that and let's see what we all get. I got about 0.039. Do we have any questions before we answer this second part? Okay, so then part B. How much money should the bank put in the ATM to be 99% certain that the machine will have enough money to satisfy a random sample of 50 customer requests? Ideas?
Inverse norm, where the probability is 1, 0, 1.
Inverse norm. In your calculator, do you have the left, center, right? Okay, what are you choosing, left, center, or right?
I didn't think that far to
Okay.
visualize this.
Okay, I love this. This is definitely an inverse norm problem. We're looking for this value right here, where this is going to be 0.99. We do not need to define x bar again because we already did that above. So this is going to be one where you would do inverse norm. I would do 0.99 left if you have that option. Mean of 87, standard deviation of 52 over the square root of 50. And we should get about $104.11.
Yeah.
Okay, now let's take a pause right here. Does that make sense? That the bank should put $104 in the ATM?
Is it per customer? Do you multiply by 50?
Per customer. Per customer. Because that's just our average. So we're going to multiply by 50, which is about $5,205.39. If this was a multiple choice question, it would probably say something like 5,210, because we're not going to put 39 cents in the ATM. How do we feel about this?
Pretty good.
This is one of those things, again, where people miss keywords or just forget that this exists a month from now. Okay. I would like you to do question 2 with the person next to you, please. So if you want to move your desk, great. If you don't want to and you just want to stay where you are, great. Good luck. This is what I would expect. Define x in words. I know it's repetitive. You have to explicitly write x is normal with this mean and that standard deviation. If you do not write this, you do not get credit.
At all.
Cannot stress that enough. You need probability notation and an answer. Of course, you would have also drawn a figure. In B, it's x bar. You need to then state the distribution of x bar. Grandpa?
For the standard deviation, do we have to write that entire notation, or can we just write like what we got from the calculator? Like
For
5
here?
Yeah.
I would show work of some type. So show somewhere that you took 5.3 and divided by the square root of 20.
Write it there. Can we just write or whatever we got?
Right, the decimal's fine. Danny?
So if I were to use, say, A as my variable, would A bar be a thing?
How'd that one go?
Good.
Okay, here's what I'm thinking. I would like to do one AP problem that we grade, and then we're going to shift to some final exam review. That work for us? Okay. Questions on this? Okay. The AP problem, I am going to have you work with the person next to you if you want to. If you want to see how you do on your own without talking to the person next to you, that is totally fine. If you go to the next page, I do not want you to do this first one. That's not a good use of your time. You will be doing this second question. And like I said, I want you to treat this like it's an actual AP problem, and we're going to grade it. So show all the work that you would on a normal AP test.
Just a quick question about the last one. Do you have to do you have to draw the graph?
Yes, for both of them. So like I said, I do want to grade this one. I don't want you to grade your own, and I do not want you to grade someone that you worked with. So give your iPad, and if you used your pen, probably swap your pen if you need to, with someone near you.
Hold up. Half the page you want to exchange or
I'll exchange.
It's easier
I'll
for you
come
to
back
grab
fast,
mine.
I'm not grading. It's in my bag. That looks alright.
As a reminder, before I show you the answer key, we're just going to look at answers first, then we will look at the grading. For each part, you're giving one grade. It's either E, P, or I. Essentially correct, partially correct, or incorrect. Just because the person has the correct numeric answer does not mean that they get essentially correct. You need to make sure that they have all of the correct work shown. Okay. Part A, the answer was about 128.4 feet. On the calculator, this was an inverse norm question. Part B, this is the one that I said sneaks up on us that we forget exists, the binomial distribution. So part B was a binomial distribution, except the probability of success is 0.3, not 0.7. Luke?
Would n equal, or,
Dude, I didn't get it.
I mean, you're not,
I wrote n equals 5.
Bro,
But it was a squiggly.
It was done in the person grading.
Is n a squiggly equal?
No, it
No.
don't make sense. He's looking at the.
Okay. And then part C was the new stuff. Part C is what we learned today. And that answer should be 0.0427.
Jesus, bro.
could this potentially be on the final one?
Damn.
0.47, not C. The
Oh,
new
so
stuff will not be on the
I
final.
got them all
Okay.
I got it wrong.
Guys, the excessive talking is so much. Let's look at grading them. Part A, in order to get full credit, the student has to indicate that a normal distribution is used. They have to write out the mean and standard deviation and give the correct value with justification.
You have to draw.
Justification would be like probability notation, a normal curve with shading, shading and labeling, of course. If the person only did 2 of the 3, that is partially correct. So in order to do all 3, they need to say it's a normal distribution, label the mean and standard deviation, calculate the correct answer with justification of some type, such as probability notation or a normal curve that is well labeled. 2 of those 3 gets partially correct.
What's the label? The distribution is normal, but you're putting it.
What is the label on the curve?
You have to write your graph in relation to yours.
Okay, part B. In order to get full credit in part B, the student has to say this is a binomial distribution. They have to show the correct value for P, which is 0.3, and then they have to find the correct probability. So, 3 parts. Saying it's a normal distribution. not normal. Saying it's a binomial distribution, labeling n as 5 as p is 0.3, and the final answer. Only 2 of the 3 will give the person partially correct. Okay, and then to grade part C, the person gets essentially correct for knowing that it's x bar and that x bar is normal, for giving the mean and standard deviations, and for the calculation. So saying x bar is normal, for giving the mean and standard deviation of x bar, and for the calculation. Okay.
What was the answer?
0.0428. A few things to note. The first one, if you have two things that compete in your work, like you say the mean is 5 and the standard deviation is 1, but then you label them differently on your graph, you will not get credit. You will always be graded on what is less correct. So if you have something that's correct and something that's incorrect, you will be graded on the incorrect portion.
That's kind of unfortunate.
And there was something else I was going to say that I forgot. So, oh, the other thing. This is not something I emphasize, but you need to know. Were you told that the distribution was normal or approximately normal? Approximately.
Oh, approximately.
You need to write that.
Really?
It has to be approximately normal.
So if the
Oh.
squiggle means approximate.
That's fine.
So when we do x squared less, say approximately normal.
That's fine.
What, just
But
like
if you write x is normal, I've seen cases where you will lose credit for that.
Who says that? Can we always just write x through line normal? Yeah.
Okay, so then let's look at grading. E gets you a 4. 2 E's and a P gets you a 3.
Oh, you were kind of-
2 E's and an I, an EPP or an EPI is a 2, and a PPI is a 2. And hopefully that gives you what you needed.
PPI is the same as EEI, right? Come on, probability.
Okay, give the person a total out of 4, and in a minute, when I'm done